Okay, for the dinosaur mobile, we know that the net torque for any particular level has to be 0. Let's start down the bottom. Okay, so we know that there is going to be a force from, let's not do that. There's going to be a force from the Tyrannosaur this way. And there's going to be a weight force from the pterosaur this way. So force Tyrannosaur. And this over here is going to be force pterosaur. Okay, so we can write a net torque equation. Those two torques have to be balanced. So I'm going to say torque from the Tyrannosaur has to be equal to the torque from the pterosaur. Or said another way, the weight of the Tyrannosaur is going to be 0.25 newtons times the distance away, which is 0.1 meters, has to be equal to the weight of the pterosaur times the distance away, which is 0.1 meters, which means that the weight of the pterosaur is equal to 0.225 newtons, which means that the mass of the pterosaur is equal to 0.025 kilograms. Okay, so we have that one. Now we can move up a level to the hadrosaur's level. Once again, there's going to be a weight force from the hadrosaur this way. And there's going to be a weight force from this whole level here. This whole thing is going to be providing, let me get rid of that, this whole thing here is going to be providing a downward force of gravity. So that acts right here, acts downward. Okay, so I'm going to call this the force from the first level, and over here this is going to be the force from the hadrosaur. And once again, we know that the torque from the hadrosaur has to be equal to the torque from that first level. So that means the weight of the hadrosaur times the distance away, which would be 0.15 meters, has to be equal to the weight of that bottom level. So 0.25 plus 0.25 would be 0.5 times 10, which would be 0.5 newtons times the 0.15 meters. That means that the weight of the hadrosaur must also be 0.5 newtons, which means the mass of the hadrosaur must be equal to 0.05 kilograms. So we've got that one figured out. Let's go ahead and work on the stegosaur. Again, the torque from the stegosaur has to be equal to the torque from all of this down here. Okay, so let's see here. There's going to be a force from the hadrosaur this way, or the stegosaur, excuse me, the stegosaur. And then all of this will create a weight force down. And it acts right here. Okay, so I'm going to call this the force from the stegosaur. And over here I'm going to call this the force from levels 1 and 2 combined. And so we've got the torque from the stegosaur has to be equal to the torque from levels 1 and 2 combined. Okay, so this is going to be the weight of the stegosaur times the distance away, 10, 20, 30, 40, 40 centimeters, so 0.4 meters, equals the combined mass of all of those. Let's see, it's 0.025 plus 0.025 plus 0.05, and that would be 0.1 kilograms times 10, so that's 1 Newton, times the distance away, which is 0.2 meters. Okay, so that means the weight of the stegosaur has to be equal to 0.5 newtons, which means the mass of the stegosaur is equal to 0.05 kilograms. Okay, moving right along to the velociraptor, we can see that there is a weight force down for the velociraptor here. And also, all of these combined together will be creating a weight force down at this point. And those two weight forces will create counteracting torques. So this will be the force of the velociraptor. And this over here I'm going to say is the force of 1, 2, and 3 combined. So we've got the torque of 1, 2, 3 combined, those levels, will be equal to the torque of the velociraptor. Okay, so what is the combined mass? It's 0.025 plus 0.025 plus 0.05 plus 0.05. Let's see, that's 0.1, that's 0.15, I believe, times 10 is 1.5 newtons, times the distance away, which is 0.5 meters, equals, for the velociraptor, it's going to be the weight of the velociraptor times the distance away, which is 25 centimeters, or 0.25 meters. That means that the weight of the velociraptor is 0.3 newtons. Yes, that's the weight of the velociraptor, which means that the mass of the velociraptor is 0.03 kilograms. Okay, now finally the last level. We've got the Styrannosaurus, or whatever that is, creates a force downward here. There would be a downward force here from all of these levels down below, all of these levels, all this stuff, and there would be a force here from the apatosaur down. The apatosaur will create a torque that is going to be counterclockwise, and the levels all down below and the Styrannosaur, they both create torques that are going to be clockwise. Okay, so I'm going to call this the force from the apatosaur. I'm going to call this the force from levels 1, 2, 3, and 4. I'm going to call this the force from the Styrannosaur. And so the torque from the apatosaur has to be equal to the torque from levels 1, 2, 3, 4 combined, plus the torque from the Tyrannosaur. So this is going to be the weight of the apatosaur times the distance, which is 0.2 meters, equals the torque from all those levels. So that's going to be the weight of all those levels. So here we have, let's see, I believe that is 1.8 newtons times the distance away, which is 0.1 meters, plus the weight of the Tyrannosaur, which is 0.14 newtons, times the distance away, 20, 30, which is 30 centimeters, or 0.3 meters. So now we can go ahead and calculate this. And we get a weight for the apatosaur to be equal to 1.11 newtons, which means the mass of the apatosaur is equal to 0.111 kilograms.